Okay, thank you. Good morning. So I'm Keith Hartington from the Delaware Valley Regional Planning Commission, and this is Meijun, my coworker and trusted colleague. And today I'm going to give you a presentation that's a little bit different. Rather than going through some of the same things that you see, developing alternatives and then giving the results, we're really going to primarily focus on our model development. We developed a large highway for an analysis tool, and I'm going to walk you through some of the latest features that we've used in Visum and Visim and the integration between the two, and hopefully you'll get something out of this. So Camden mentioned just a few minutes ago the Delaware Valley Regional Planning Commission, which is the greater MPO for the Philadelphia region. We're bisected by 2 states, Pennsylvania and New Jersey. We have 9 counties, a lot of municipalities, a lot of people, and nearly 1 million developed acres. We're located, Center City, Philadelphia is located about halfway between Baltimore and Baltimore and New York. And actually the Delaware River divides the 2 states between Pennsylvania and New Jersey. We have 4 counties on the New Jersey side and 5 counties on the Pennsylvania side, with Philadelphia there right in the middle. How do we get the little mouse guy? How do we get the little red dot to come up as a pointer? What? How did you? Oh, this is it.
Yep.
Oh, okay. Is it?
Pick a laser.
Oh. Laser.
Yep.
Yes. Okay. Thank you. Sorry for the delay. Okay. So for this particular project, we were commissioned by the Pennsylvania DOT to develop a large highway model in a suburban area of greater Philadelphia. And essentially to assess the existing conditions and the future conditions that we're taking a look at, and also to use this model in the future to do some sensitivity testing with some build alternatives. And so what we wanted to do was model the entire corridor as a system. So it includes the main line, the interchanges, the auxiliary lanes, the merge and weave diverge areas, the ramps connecting to and from the facility, and the signalized intersections at the base of the ramps, and a very small portion of the local facility. So we wanted to develop, the goal is just to develop a holistic type of model that would represent traffic under prevailing conditions. So here's a kind of a geographic sense of where this corridor is located. It's kind of north and west of greater Philadelphia, between just bisecting Montgomery County there, and actually the very last portion there is in Berks County, just adjacent to the DVRPC region. Here's a little more a zoomed in area. Overall, the highway is approximately 25 miles in length, contains 15 interchanges, primarily 2 lanes in each direction, and has a consistent 55 mile per hour speed limit throughout. And I will mention that down in this section down here, you have King of Prussia, a large mall, higher population and employment centers, and so it's kind of oriented in further points beyond here, down into the city, where you have a lot of jobs and so on. And then towards the opposite end there, it becomes more rural and less dense. So the project objective really boils down to 3 major tasks. The first of which was to develop a base year, which it was a 2018 existing conditions model, and a no-build operation model, which will represent a 2040 condition. The build scenarios, we want to test improvement strategies that could include any type of small widenings, interchange reconfigurations, perhaps a signal timing at the end of a ramp, or ITS applications such as ramp metering or hard shoulder running. So we have a wide menu of things that we could potentially take a look at. And then obviously we want to collect performance measures across those scenarios to really understand if we're testing a local improvement, Does it relieve the congestion in a particular area? Does it reduce congestion overall? Or does it simply push the congestion or problem up or downstream? So that's the purpose of having a holistic type of model that will be able to test those types of improvement scenarios and deliver some results. So this is just a basic project timeline. It's a 3-year study. We're about halfway through it right now. For the most part, 2018 was reserved for data collection, which I'll talk about considerably more in just a few minutes. And then we're just now into developing the no-build scenarios. And then later this year, we're actually just having a steering committee meeting at the end of the month to talk about the build scenarios that we're going to develop and test, and eventually get into a final report and some type of final deliverable. So I mentioned there we have a steering committee meeting coming up soon, and then probably another steering committee meeting for when we kind of present our findings from what our outcome is at this upcoming meeting in terms of what we're going to test. So here's just a snapshot of the volumes. Graphically, it's not to scale. We've separated the eastbound and westbound lanes dramatically. They're not that far apart, but just for graphics display, it's easier to see. And you can see like the volumes are much higher in the southern and eastern portion of the study area, and then as you move up out into the less urbanized areas, the traffic volumes decrease proportionally. So temporally, you see this. I'll take you through the morning and PM peak hours. You can see the traffic in the morning oriented the eastbound direction from 6 to 7, 7 to 8 as we move through the morning. It continues until finally it starts to subside between the 9 and 10 o'clock hour. In the westbound and the PM, you see the traffic volumes are much higher. We have a lot more congestion in this particular direction. This is 3 to 4. And then moving through the PM, you see some darker red there before finally kind of dissipating in the last hour of our model between 6 and 7. So I mentioned we did a pretty extensive data collection effort to develop our model, including 25 manual turning movement counts at the base of the ramps throughout the study area. Collected 40 ATR counts on all of the ramps that fed into and out of the facility. We did 28 mainline counts at various sections to get some good mainline volumes. And we also did 14 classification counts so we could really calibrate and understand the percentage of heavy vehicles, and not only just the percentage, but we grouped them into 2 different vehicle types for our VISIM models. So there's other data collection. We also got the traffic signal timings from the DOT. We also have DVRPC, a very large and robust historical count database, which we use for quality checks of all of the new counts to cross-reference to see some of when we're doing smoothing and balancing, we can look up historical counts to make judgments about which count may be right. We also mined the INRIX data set extensively. We pulled out 1 year's worth of data and into a large database. We pulled out every Tuesday, Wednesday, and Thursday for an entire year. And that helped us with our speed calibration, which I'll talk to more in a few minutes. And also we got some LEHD data, which also helped with calibration, which I'll speak to in just a couple minutes. So I know if you were at this session yesterday, talk about getting rid of spreadsheets and doing things differently, but for this, our spreadsheets were very helpful. So we have traffic counts from a number of different sources counted on different days and times, and it's large for 25 miles in each direction. And we wanted to make sure that we had a really good and robust and calibrated vehicle or volume inputs into our model. So we first started looking across the entire peak period. That was from 6 to 10, and just doing some basic arithmetic spreadsheet calculations for the main line in each direction, adding and subtracting the ramps. And that kind of was our first level of balancing the traffic volumes. And then secondly, we delved down into the individual hour both for the main line, the ramps, and we also introduced the signalized intersections at the base of the ramps. So all three would be in sync and fairly balanced, and this would serve as our inputs to T-Flow Fuzzy, and it also serves our target volumes as our output from VisSim. So this is just a quick picture of the DVRPC regional model. See, it's over 9 counties. It's a fairly robust model. Contains over just about 2,500 zones, over 500,000 links, and just over 200,000 nodes. So it's a very robust model, to say the least. So from our regional model, we did our subcut, and this is the results of the subcut. We just simply took the main line, the ramps feeding into it, and also a very small segment of the local facility at the ends of the ramps. So we would have each approach from that intersection feeding into our network and then eventually feeding into the ramps and then onto the main line. So this was just the original output from VisZoom, and in terms of our calibration without doing anything. From the 8 to 9 peak hour, and you can see the link volumes weren't too bad, but the turning movement counts were kind of all over the place. But we don't really expect to see, really calibrated, finely tuned peak hour turning movements in a regional model that large. So we had some work to do. So the first kind of step in the calibration, this was just after we ran T-Flow Fuzzy the first time around and had entered the link volumes into the network to get output from this. This is where we brought in the LEHD data. So what we did was we aggregated that data from the census blocks into territories, and then we imported that layer as a geographical interface into VisZoom, and then we were able to better calibrate the volumes feeding into the intersections at the ends of the ramps. Does that make sense? So rather than, the problem was that out of VisZoom, a lot of the ramps or the intersections were fed just from approach from one direction, but that was just a function of how the zone structure was set up. So we wanted to refine that and make sure that we had good data after that. And as you can see, the T-Flow Fuzzy exercise, after we did that balancing and calibrating, we hit our targets really well. So this is just within VisZoom, and we were able to achieve a very high level of calibration. But again, we had a very balanced set of data that we were inputting and our targets were trying to hit. So once we cleaned up the links at the turning movements, we had good success. So here's a snapshot of the VisSim model. You can see the eastbound and westbound direction are not nearly as far apart as you saw earlier. So this is just kind of the overview of our VisSim model. And I also want to talk about, we also explored the coordinates-based routing. I don't know if folks have explored that just yet. We had the idea of going with the dynamic traffic assignment to build our route structure from the beginning. But we got word and wind that the coordinate space was easy to use and fairly user-friendly, so we went ahead and gave it a try. Maybe it was going to work out better than DTA. So we went ahead and did that, and we got, the process was fairly intuitive, it was straightforward and pretty easy. The problem was on our end, because there were a couple of geometric changes based on some interchanges that were being reconstructed. So the output from VisZoom did not match our VisSim network. So there ended up being a lot of routes that were missing. I think we had exported about 800 routes total, and there were about over 100 missing, and we would have had to manually enter those in. So we decided to stick with our DTA. So here's one of the reconstructed interchanges at the southern end. So this ramp here is no longer exist. This is now a flyover that you see here. And at the northern end as well, there is a, This trumpet, if you will, trumpet interchange, that is no longer there. It's been reconstructed and redesigned also to smooth out this curve into a more tight diamond interchange. So that was why we ended up not using the coordinates-based routing, and we stuck with our DTA. Here's just a picture of the completed interchange. This was taken over the summer. All of the construction for the interchange there has been completed. So this is probably one of the more important slides in the presentation here. So I'll walk you through how we did our DTA. And out of the Vizum regional model, we have a trip table that's for the entire peak period, from 6 a.m. to 10 a.m., and then in the afternoon from 3 to 7. So we factored our trip table to get individual hourly trip tables from 6 to 7, 7 to 8, and so on. And we basically factored that uncounted data. And so once we had the individual trip tables for the individual hours, we then put those into the SIM network individually. And we entered the target volumes and turning movements for that respective hour, and then we ran DTA for each of those hours, and we did some light level calibration, and then we were able to stitch those 4 individual trip tables out of this SIM into one larger SIM network, and then we ran DTA for the entire peak period. Is that kind of, it's kind of, if you have any questions about that, I can clarify. But so that was kind of our systematic approach to do it individually. For the hour we ran DTA, then we kind of put those trip tables back, and then we did DTA for the entire 4-hour peak period. And then we were able to summarize the model results. One of the things to always be careful of is the route closures in VISIM. Sometimes in Vizum, the shortest path is to get off an interchange and then to get back on because there's some congestion on the main line. So there's cleaning this up it's important to be aware of this. That's one of the things that we saw. And as far as like the travel speeds, I know there was some discussion earlier about calibrating for travel speeds. We mined the INRIX data set. It's a very, very detailed and robust set. We pulled out gobs and gobs of data. And luckily for us, the INRIX segments are smaller than our links in between our interchanges, so we were able to aggregate those together. And what you see here is basically like a speed profile from a particular location across the day. You can see the speed slowing down in the PM because of congestion. But you don't want to get into the habit of putting in desired speeds to force your traffic to slow down based on congestion. So we wanted to enter the free flow condition and then let the congestion and then the friction between the vehicles at the interchanges and so on slow down the traffic kind of as you would in reality. So we pulled out and aggregated the travel speeds in both directions between all the links, and then we input that basically the free flow condition. And we did also include the percentiles for the 5th, 25th, and so on, and for both directions. And then we ended up with a distribution for a particular segment. If there were segments that had similar speed profiles, we simply used for multiple sections rather than doing every single section just for time savings. So here's kind of that overview of the congestion scan. You can see primarily in the eastbound, you have the congestion slowdown at the southern and eastern end, which we saw is related to the volumes. But for much of the corridor, or at least from the northern section on in, and in the westbound direction in the morning, it's pretty clear. It's not, we're talking 40, 50 miles an hour. It's not too bad. In the PM, kind of the reverse is true. We have the outbound flow in the afternoon. The slowdown is in the southern end, kind of heading out from the city and the population areas, whereas the eastbound is relatively free flow. I will mention at the at this section here, there is one signalized intersection at the end of our network where the limited access ends and it becomes like a local access facility. That's why you see some red there at the very end. So it doesn't look too bad, right? So we're starting to see these bumper stickers on folks' cars. Apparently a website has started up of these grassroots angst, 422 sucks. Well, I can understand that somewhat, but a lot of this is probably more perception than reality. But if you're just getting on here and then you're getting off here, you're in that traffic every day. So you're driving 12, 15 miles per hour for several miles, and it can be very frustrating. So and as you see, sorry, let me go back to this one more time. Today, this is as 2018. The congestion isn't too bad, but especially in the lesser developed central and northern sections of the corridor, we're expecting about roughly 1.5% growth per year for the next till 2040, which translates into about 30%-ish growth between now and 2040. So that's some substantial growth. So we're not just preparing for today, but potentially for what we're going to see tomorrow. So here's the output from our VSIM model between 8 and 9 a.m. Not too bad. We're well in the GH statistic. Again, I attribute a lot of this to the data collection and our spreadsheet operations, and we made sure we had really good and balanced volumes into our network all the way through VSUM into VSIM. So when we get to this point, it does save you some time when you're not guessing which volume is right or why you have issues and so on. So it helps to do your homework up front. Travel times, like I mentioned, westbound, even into the PM, our slowest time is in the upper 40s, which doesn't sound too bad. That's end to end, so it's kind of weighted because a lot of the corridors at free flow conditions, and even though it's a posted 55 mile per hour, most people are going 65, 70. So you don't get into the congestion until the southern end. And again, it may be just more of a perception, or if we did these travel times for shorter segments where the congestion, where we would see much different results. But end to end, it's not too terrible. Collected level of service data at the signalized intersections at the end of the ramps. As you can see, even though the mainline facility carries a lot of volumes, it's not too bad on the local facility, at least accessing in and out of the facility. We don't see too much issues. That's in the morning. But in the PM, mostly A, Bs, and a couple of Ds. But again, we expect a lot of these, as the volume increases, the ramps are going to, volumes are going to increase, the turning movements at the intersections are going to likely decline. And although we haven't got to our no build scenario yet, we're working on it. We'll likely see a lot more Ds and Es and maybe an F or two. So just some nice graphics. Camden, used these and they're really good for storytelling. This is just a snapshot of the volumes. And then our speed profile, you can see in speed 5 mile per hour speed bins. These are really nice to show folks for a quick snapshot of your speeds and your conditions, especially at this scale. If you zoom out, it's not as effective, but at this scale, it's really nice. The flow bundle in VSIM 11 is really helpful, not only to show you your O&D distribution, but also how weighted a particular OD is by the line thickness, which is really great. And some of the static 3D models in VSIM 11 are much easier to use than in previous iterations, and thanks to PTV for helping with that. We did some really nice, it's really easy to do these type of graphics and so on. So so as far as where we go from here, so I kind of walked you through what we've done so far. Essentially, we're finishing calibration on our existing conditions model, and then we're working on the no build, and then eventually to some build conditions. And primarily, we have a pretty good idea of what the DOT and the stakeholders are looking for. We're getting word that hard shoulder running or some flex lane applications is desired in this corridor. perhaps some limited widenings or so on, but the ITS components, I think, are being explored on other highways in the Philadelphia region, and we can see this easily being utilized on 422 as drivers in the area become more familiar with these types of applications and so on. So that's all I had. I hopefully got something out of this, and if we have any questions, I think we have a few minutes to talk about questions. We have a short video that we'd like to show as well while I'm answering questions, if we have any. Well, yes?
Is that picture of the van your van?
No. Meijun took that picture. Where was it? In a parking lot somewhere. But yeah. Again, if you're commuting in that every day, I can understand. And it's not just 422, because 422 feeds into 202, and you have access to the Turnpike and 76. So that is just your start of your angry commute. So if you're commuting from that point all the way into the city, you can expect another 45, 50 minutes of bumper-to-bumper traffic. And so I think 422 gets a bad rap because of that.
So,
yeah, go ahead.
Sorry, real quick.
No, that's okay.
On the DTA, so you ended up with the hourly matrices.
Yes.
Once you got your DTA converged, did you extrapolate that to like 15-minute profiles, or did you keep those up?
We kept them in the hourly profiles.
Okay.
Yeah.
Did you at least evaluate what the actual peaking profiles are in the field? And
We had hourly counts which we were measuring them against.
okay, so you didn't have count data with more resolution then?
No, we kept everything to an hour. Yes, for better or worse. We've done down to a 15-minute increment in the past, and it just became overwhelming because it's just a lot of work. So we just kind of kept it to an hour. Yes, Ms.
So I see the speed profile or the travel time that you guys looked at. Is it like historical or that year, or what's the time duration?
For which, do you want to?
So kind of a contour plot that shows the travel time, or actually the speed is like 38 and 39, and it goes back up. So as you're saying, it's not actually that bad. It's more of an experience. So is it based on a historical travel time, or is it based on like year or like 2018?
From the INRIX data, is that what you're asking
Yes.
about? That was all from, what year was for that from?
2018 to 2019.
Okay, so it was 2018 and 2019 data.
2018 to 2019.
Yes. So we tried to pull out as.
Yeah, kind of.
Oh, this?
Which one?
Or the.
This one kind of shows the congestion after the results and all.
Right.
But I was talking about the INRIX data that you guys pulled. So you guys had 1 year data, right?
Yeah, we did. We basically pulled out every Tuesday, Wednesday, and Thursday for an entire year. We didn't look at like on day where there was an event or a large crash, or maybe it was a holiday or whatever. We just figured that if you just want to build a typical, that all gets washed out. Some days are light, in the summer the traffic volume may be a little lighter, or so on. So we just pulled out an entire year's worth of data, and we figured that would be a sample size large enough to kind of find the middle ground.
Yeah, that sounds good.
Okay. Okay. Oh, yes.
So was there particular, why did you then model that, like you said, like a significant portion of this corridor is, green?
Right.
Why model all that area instead of just concentrating on it?
Well, actually, I want to look back. Oh, here, this is good. So you have your population and employment centers down here, and then Philadelphia is further down. And this, especially in this neck of the woods, the municipalities are growing at a pretty fast rate. So I guess to get out ahead of it, like I mentioned, we see overall between now and 2040, we can expect a 30% increase in traffic. So now as the queues are, kind of maintaining this area, we expect them to grow and build further back. And I think they want to get out ahead the DOT and show, this is what's going to happen. This is just the trend line. If development keeps happening and it's, suburban without any thought to incorporating transit or those types of things, this is hopefully will, kind of send a message that if we keep doing things the way that we've been doing them, this is what we can expect.
So in the future, the stickers would be whatever that is, sucks even more.
Or maybe they'll just move. Yes, yes. This is citizens these days. They demand a lot and don't always have a full grasp of the issues involved to solve these problems. But we'll see. Yes, ma'am.
Can you talk about the DTA a little bit more? I wasn't clear on, you imported the 4-hour or 5-hour, whatever it was, matrix into Vism and then generated just a single hour?
Yes. Well, within Vizoom, we factored our trip table
Yeah.
from a peak period to a peak hour. So we had some numbers over here out of the model for each individual hour,
Yeah.
and based on our real counts. So we were able to multiply by 26% to get 6 to 7, or 24% to get 7 to 8, and 22% to get, I'm just making these numbers up.
Yeah.
So that produced then we multiplied the entire trip table by the one factor. And that gave us 4 individual trip tables,
Okay.
from which then we ran the DTA
You
individually.
calibrated each hour separately.
Yes, yes. Just like loosely calibrated, just really for volumes,
To
just, yes.
verify.
And make small changes and tweaks to the trip table before we brought them back together.
Got it.
Okay? I guess we're about time for lunch. We have 2 minutes. I guess good enough. Anything else?
One last question, maybe for the 2 minutes that I've